Right, people, it's 1 sharp, so it's my pleasure to start the afternoon program. And I can tell you something about the ICFP contest that I organized this year together with some other people. So just a quick recap for those who may have forgotten or may not have heard of this, but the ICFP contest is a 72-hour programming contest held every year. This year it was held at the end of June. Every year there's a new bunch of organizers, and the main goal is having fun with functional programming. Like most years, this year there were no monetary prizes to be won. The contestants did it pure for fun. However, as a prize, I, as the main organizer, will make some statements about the programming languages used by the contestants. So it's used as a bit of a competition between programming languages, you could say. So speaking of which, I decided to take a bit odd order maybe, but I will first present the results of the contest and then tell you something about the program that these people solved, just to get this over with. So I can announce that Spreadsheet and Rust are very suitable for rapid prototyping. So teams Manarimo used Spreadsheet and teams Unagi. They were tied after exactly 24 hours in the contest. This took only 15 minutes or so that they were both on number 1, but they both won the lightning round, so congratulations. And then for the first prize, I can say that Rust is the programming tool of choice for discriminating hackers. So again, Team Unagi, congratulations for winning the contest. For the second prize, yes. For the second prize, I can say that OCaml is a fine programming tool for many applications. Congratulations to the Y Combinator team. Yeah, so I will explain their team name later. So it's the Y Combinator, but written inside the language that we used for this year's contest. So a very nice team name. And they used also not only OCaml, but also C++. And then finally, C++ is also not too shabby. So congratulations to the team Purely Functional Networks that also used a bunch of other languages. And then finally, there is also a jury prize. And this year, I can say that Team Panicked Albatross are an extremely cool bunch of hackers. So congratulations to that team as well. The reason that we picked this team is that they were just 2 persons still ending up at rank 33 out of a couple of hundred of teams, so that's quite impressive. And they had a very best score for one of the problems that we called 3D12, and I'll come back to that later. So one hand for all the winners again. So, the problem, what did we as an organizers let contestants do this year? So we made some design choices up front to decide on what properties the contest should have, and the number 1 property was it should be fun for participants. It's tied to the ICFP, to this conference, so we did want some connection with functional programming as well. So historically there have been problems where they say, well, you can also solve it with functional programming, but we were hoping for something with a bit stronger ties to functional programming. It must be challenging. There's very good teams out there, and we must make sure that people, well, stay interested for 72 hours, which is actually quite long. We also want a low entry barrier. There's always teams doing this for the first time, so they should not be scared off. As a contestant, we always enjoyed having a live scoreboard so that it's competitive and it's interesting then to know during the contest how you're doing. We must run it, we must maybe set up some servers, so we must be able to manage that. And then finally, we wanted a permanent artifact for the future. So the contest is 72 hours, but there's a whole history of these contests. And it's nice that you can look back in maybe 10 years and look at the problem and still play around with this, which is something I did with some older contests. So then, based on that, we tried to come up with a storyline, and we based it on some previous editions of the ICFP contest that we really enjoyed, which were from 2006, 7, and 2020. So in 2006, the storyline was that there was an ancient group of people called the Cult of the Bound Variable. And in 2006, the Cult of the Bound Variable was long gone. But in our new story, it turned out that they moved to space. And they used what we call interstellar communication functional programs to communicate, which we'll abbreviate with ICFP, which is a special programming language that we designed for this contest. And then communicating with this cult, the contestants of this contest had to follow some courses in some school and pass some tests. And in the rest of this presentation, I will call these subtasks and problems. Because the whole contest is set up in such a way that we have sort of orthogonal set of tasks, each featuring a set of problems. So this ICFP language, in the problem statement for contestants, I explained it in more words, but here I can just say that it's a pure non-strict dynamically typed functional programming language, so lambda calculus based. We have Boolean, integer, and string values. We use a call by name evaluation strategy. However, it's non-human readable. So here's an example expression. And we did this by design so that we forced the contestants to at least write their own interpreter, evaluator, and such. So it's space-separated set of operators. I'm not going into the details here. There's a nice website where you can read all of this. But the B is the binary operator, so it's prefixed. So the dollar is application. So this, in some more human-readable form, would be this expression. And as you can see, also string literals and integer literals are obfuscated, not in a very complex way, but so that you at least need to write some code to be able to read these expressions. And this language is used for all communication. So anything between the contestants and the server would start with this language, and then you send something and you get back something. And this is how contestants slowly discovered more challenges to solve. And the very first one we called hello was just to get contestants started with the system and understand how this interaction works. And in the problem statement, we explicitly mentioned this, S prime something something string, which is mentioned at great entry point. If you implement the string encoding, it translates as get index. So if you send this ICFP expression to the server, you would get a long string back, but ICFP encoded. In this presentation, I've decoded it for you, and it would read this text. I will not read it out loud, but it's a small index page explaining a bit what kind of operations there are. And here, contestants had to realize that you did get index to get this page, so that you can maybe also do get scoreboard or get language test or get echo. So in the hello subtask, you could score points for doing this. So get scoreboard would give you a string encoded version of the scoreboard. There's get language test, which would give you a big expression evaluating just to a simple string in the end, but you had to implement all operators in the right way. So it's a sort of self-test for your implementation of the language. And then the echo service is just sending back the string that you sent, but you could later on also use it to check the server implementation of this language. So for example, if you want to know how integer division rounds, you could construct the ICFP expression, which we can write in a more readable language like this to check if it sends back yes or no. And in this case, it would send back yes. So this was just to get people started, to make sure that people could end up on the scoreboard quite soon in the contest. Now the first real subtask that we presented the contestants with is called Spaceship. And it's based around the idea that you have a new chess piece, which is called Spaceship. The spaceship has state, it has speed Vx and Vy, so horizontal and vertical speed, both integers. And each move, you can change these integers by at most one. So you can increase them or decrease them by at most one, each independently. So there's 9 possibilities for changing them. And then the spaceship moves Vx and Vy steps on an infinite chessboard. So the first move that you make is basically like the king in chess, so you can just move to each adjacent square, but then it has gained some speed, and then the next step you could move a bit further by changing its speed. So it's a bit, how do you say this, inspired by how spaceship movement works, but then in a discrete world. Now the problem is, given a list of target squares, target locations on an infinite chessboard, find a minimum length sequence of moves. So you submit the moves that you need to do to get this. So this is a kind of an optimization problem where we also, as organizers, did not necessarily have a very good approach, but it turned out that simulated annealing, for example, worked. So contestant did all sorts of approaches here, which I will not talk about more now. The next task that we set for the contestants we called Lambda Man, based on an earlier version of the ICFP contest 2014, if I'm not mistaken, where the whole contest was revolving around Lambda Man. This time we had a very simplified version, so you have a two-dimensional world. There's a Lambda Man, which might resemble Pac-Man. There's some pills, the dots in this picture, and there's some walls, the hash symbols in this picture. And you need to find a sequence of moves to make sure that all the pills are eaten. The score, however, is the length of the ICFP expression that you submit. And this is a crucial thing here, because it might at first glance look at a somewhat similar problem, where you need to find some sort of minimal path. But actually, you did not necessarily need to find a minimal path. You need to find a minimal expression. However, these expressions are written in this lambda calculus-based language, which is Turing complete. So actually, you had to find the smallest expression generating a string that would eat all pills. So to hint at this, we actually also, as one of the problems for this problem, gave the level which is Lambda Man followed by a long list of pills. And then the best solution for this is the ICFP, this kind of expression. So it just replicates a lot of R's. And this expression is actually much shorter than 200 characters, or 199 characters, while the obvious string solution for this would be 199 characters. So this was a bit of the wow effect for some contestants, where we got questions like, hey, people have this low score, but that's not possible, right? You need 199 steps. Well, yes, but the expression does not necessarily need to be this long. And then we iterated on this idea and made some harder problems as well. So we have some mazes where the path is a tree-shaped form. We created some fractals where you really can, if you do it smartly, construct a very small expression to exactly visit the whole path. And we also generated some problems by making a small expression with a pseudo-random number generator, just linear concurrence based with small constants, so that you could even try it or guess it, which people did. To our annoyance, they did it better than us, so they made even smaller expressions than the ones that we started off with. So we've also written a report, which I will publish later today, and we got some more information there. Then the third of the four real subtasks that we gave them, we call them efficiency. And the idea is very simple. You get from the server an expression in this language, which evaluates to an integer, and you have to submit that integer. The storyline said something about the cult of the bound variable somewhere in space having a quantum computer to evaluate this. But unfortunately, contestants do not own a quantum computer. And it was hinted at that just having a fast evaluator might not be enough. And it was certainly not going to be enough. So on purpose, we constructed expressions that would not easily terminate. So the intended approach here was to at least pre-print these expressions, reverse engineer them, and maybe in some other ways construct the right answer. So for example, we started off with some expression where you have just a number plus some very slow expression times 0. So if you pre-print it and realize this, you can just submit 2, 1, 3, 4. We computed the 40th Fibonacci number, but in the exponential way. So if you just try to evaluate it, it will take some time. Linear search for the next Mersenne prime bigger than 1,000,000, which is also quite a bit further in the list. And then, of course, with a linear stupid prime check in there. We had some SAT problems in there where we just implemented the brute force try all possibilities solver in our language, Sudoku solver as well. fortunately, teams did find the answers to this. Some of them mentioned that they solved the Sudoku one without realizing it was actually a Sudoku, but they just saw like a big iteration and then some checks on numbers, and they just used an SMT solver to solve this without realizing what it was actually computing, but they found the right answer, so that's nice. And then the last subtask that we presented them with, we called 3D, and this is a esoteric programming language that we designed based on the 2D language from 2006, which we really enjoyed. So we really wanted to call some problem 3D. It might look 2D, but the name later on will be clear. Let me first give you a very quick example of how a program in this language looks. So it's a 2D grid of things, and the little arrows, so the bigger than, greater than signs, move things across the board. So, and then the numbers move. So if I move my slides, you can see a small, low-tech animation here. So the numbers move. And then the plus operator resolves only when there's inputs on the left and the top. So the 3 and the 1 are now there. So then it computes a 4. And then finally, this 4 moves to the S, which is submit. And then this program submits 4. And the thing that we compute the score for a program is its 3-dimensional size or its volume. So it has 2 dimensions and it has a time component. So the number of steps the evaluation took is the 3rd dimension. So it's a 2D grid with reduction rules. The values are all integer. Operators reduce when both values are present. And as I said, the score is the volume. However, there's a very important thing that I did not mention yet. We also had an operator at, which is the time travel operator. And this time travel operator lets you go back in time and then replace some values. So the whole board would be reset to a given earlier evaluation step, but then with one number replaced by a new number. So this allows you to make loops, and this gives 2 things that you can use. So you can make loops, which is nice. You can also already in 3D make loops by letting numbers go around, but this is a new version of a loop. And it can also help to limit the time. So the score is based on the maximum number of time reached, but if you go back in time, then... with this language, you can make constant time loops. And then we were giving a set of relatively standard programming exercises to be solved within this language. But let me first very quickly show you an example of how this looping works. So this is a program. A and B here are input. So if you call it with test, we provided some test command. The A and the B will be replaced by the inputs that you give, so 3 and 4 in this case. So these are the steps that the evaluator take, and you don't need to really get all of this, but I like the animation effect. So there's 2 time travel operators here, and this actually computes 4 times 3 in a loop way. Actually, we provided the multiplication operator as well, but let's say if you don't have it and you want to do it this way, then this is how you would do it. So we have the 4 moving several steps, and then it became a 3. And now the 2 time travel operators have their input, so they have a dx, dy, and a dt. So they have some components, so they both reduce at the same time. And we go back 3 time steps, which is exactly t is 1 again. So we're back to almost the same thing, but one of the numbers has decreased by 1, and the other number is sort of the accumulator that is now the sum. So we do this again and again. And again, and now you can see that there's 12 somewhere on the right, halfway, and the number in the left top has become 0, so the loop is sort of finished. And now the equal sign all the way on the top reduces with the 0 check, and this makes the computation submit 12. No worries if you didn't fully get that, but the idea is hopefully clear that you can do time travel. And this program took only 4 time steps, because we went back in time all the time. So what did we let the contestants solve? So we had a factorial, the absolute function, the sign, which are tricky because we did not provide comparison operators. So you could do not do smaller than or bigger than. So that makes absolute and sign and maximum a bit tricky. Least common multiple, primality and palindrome check, so palindrome on numbers. find the smallest number b such that a in base b is a palindrome. Matching parentheses, so the input would be a number consisting of 1s and 2s representing parentheses, and you have to output a 1 or a 0 indicating whether or not this string of parentheses was well balanced. The same, but then with 2 types of parentheses. And then we get to the somewhat trickier problems. Well, they're all tricky if you consider that you have to program in this esoteric language, but we took it further and then given a lambda man path, which would be like the 4 directions, so the 1, 2, 3, and 4 would be the 4 directions that you go, count the number of unique squares visited. So this represents some sort of path where you walk in the 2D grid. Some squares are visited multiple times, so you have to count how many unique squares are visited, which is tricky if you consider that there's only very limited state and so on. And then 3D12, which I mentioned before, for which we gave away the jury prize, was compute the sign to a certain number of decimals. So we scale it so you can approximate the sign function with some methods with all integral values. So we just scaled it to 10 to the power of 9. So you had to compute it from the input number up to this number of decimals with some error margin. I will not explain the next 2 slides to you, but I would like to show you the best results for 2 of these problems. So the factorial function can be implemented like this in this language. So in principle, it's similar to the multiplication that I showed to you before, but then really compactified in the minimum amount of space possible, I think. And then approximating the sign function is done like this in 3D. If you want to know how this works, the team also wrote a very nice write-up to explain it. Then finally, some small words on scoring. I said we have 5 different subtasks. But they're not all the same. Some of them have sort of a binary scoring. You either solve the problem or not. The other ones have scores that can range from maybe millions, like a spaceship set of moves, to maybe tens of points, like a very short answer. So we were playing around with this a bit. In the paper we explained this more, but in the end we came up with a scoring function where the teams are candidates in an election and the problems are voters. So the better you rank in each problem, the more votes you get from that problem. And then we use the so-called board account to combine all the teams. And this boils down to, for each problem, the amount of points you score is the number of teams strictly worse than you. And then we sum these over the problems. This led to a very nice way of dealing with ties and also making sure that there's not a single subtask where you can do so well that this dominates the final score. So to be high on the scoreboard, you had to be good at each of the subtasks and not just very good at one. So we completely ignore the absolute value of the scores. It's only about order of the scores in each subtask. And then we showed the scoreboards also on the website. Yeah, and we disclosed this. So a few statistics. We had 470 registrations, though there were some obvious duplicates in this list. 365 teams did send in some message, so some submission, of which 355 got a non-zero score. So there's unfortunately 10 people that did some attempt but not get much further. In the whole contest, about 200,000 messages were sent, of which, well, a third scored points. This is because getting a problem was, but also a message sent, so that's to be expected. And we asked in a survey afterwards, how much did you enjoy the contest? And on a 1 to 10 scale, we got an 8.7 from the contestants out of 55 responses. I don't think I'll read the list, but these were some commands we got as input, which I enjoyed. None of these worked, but I especially liked get space shit. I'm not sure if this was on purpose by a team being completely done with the problem or not. Yeah, but we got it. Then to wrap up, I would like to very quickly thank some people. So Matusz for being my co-organizer and doing a lot of work. Bas for nice inspiration. Emerick, who organized last year's contest, for the mentoring, and then some other people that helped us. And of course, the ACM Sigma conference on functional programming for sponsoring. So I hope to see you next year as a contestant. Keep an eye on the website. We are looking for people that would be interested in organizing next year's contest. I will be mentoring for next year, so I will be involved, but I will not do the main organization another year. So if you're interested, please come to me. I'll be here today or tomorrow, or email me, and then I hope to all see you next year. Thank you very much.